4.3, derivatives of inverse trig functions.
Are these more like memorizing?
Yeah. I'm going to derive some things for you,
Okay.
which is why it's so long. But yes, ultimately you'll be memorizing the 6 inverse trig functions.
Okay.
All right, theorem 1. Derivatives of inverse functions. If f is differentiable at every point of an interval I, and df dx is never 0 on I, then f has an inverse, and f inverse is differentiable at every point on the interval f of I. I think before I derive any of them, I'm going to go ahead and give you all 6. So in the event we don't get through everything today, you've at least got what they are so you can start memorizing them. Because hopefully next Tuesday we can quiz on 4.1 to 4.3. So that way we get that quiz out of the way before break. So I'm going to go ahead and do that, what I normally would do them at the end. And then we'll derive some for you. So all 6 inverse trig derivatives d dx of the inverse sine of x is equal to, and it would be the same thing if it's written as arc sine or the sine to the negative 1. It means the same thing, just FYI. Is equal to 1 over the square root of 1 minus x squared Now, I'm going to intentionally line these up different than we normally would, because normally I do sine, cosine, tangent, and so on and so forth. This time I'm going to do sine, beside it cosine, and you're going to see why in just a second. So then d dx of the inverse cosine of x is equal to negative 1 over the square root of 1 minus x squared. So what do you notice about that?
It's the same,
Like the same but negative.
negative.
Same but negative. Then d dx of the inverse tangent of x is equal to 1 over 1 plus x squared. So then d dx of cotangent, or inverse cotangent, which normally we haven't really dealt with inverse, secant, cosecant, or cotangent, just because there hasn't really been a need to this point. But they do have a benefit. We still won't use them very often, but it is negative 1 over 1 plus x squared.
I'm seeing a pattern.
And then d dx of secant, or inverse secant of x, is 1 over x times the square root of x squared minus 1. And d dx of the inverse cosecant is negative 1 over x square root of x squared minus 1. Bet you wouldn't have guessed that was going to be it, huh? Now, I'm going to go ahead and warn you before I get into deriving them that these can also have chain rules applied to them. Okay, so what's inside for x could potentially cause a chain rule. So as we use them, this will make more sense as to what I'm saying, which I know we always say that, but you have a new cast.
Yeah, I don't know.
Just looked down and I was like, it's green. Whoa.
It's always been green.
It's infected.
That's not good. That is not
Is
good.
it smaller?
Yeah, it's like longer this way though.
That means all of us can re-sign class.
Only 3 people signed it at the first.
Anyways, squirrel. But yeah, just to give you a heads up, we will be doing more with it than just this. But you will need to memorize these. But again, I lined them up intentionally so that you could see the pattern with them because, you know, it's oh so nice. So, next thing, I'm going to do basically explain the derivative of arc sine, which is also known as the inverse that way. So x equals the sine of y is differentiable in the open interval minus pi over 2 less than y less than pi over 2. And its derivative, cosine, is positive there. Okay, so from negative pi over 2 to pi over 2, would you agree that cosine is positive? So basically on the right side of the unit circle.
Yeah.
Okay, x values are positive there, so that's why it's saying it's positive there. So, by theorem 1, y equals the inverse sine of x is differentiable through negative 1 less than x less than 1. But it can't be differentiable I'm going to abbreviate that because I'm tired of writing it out. At x equals negative 1 or x equals 1 because the tangents of the graph are vertical at that point. Okay, meaning they're undefined. So now, to actually take the derivative, the derivative of y equals the inverse sine of x we would start with the sine of y is equal to x. Which is an inverse function relationship. So if we take the derivative of both sides, okay, with respect to x, we would have the cosine of y, y prime, is equal to 1. And so this is, we're differentiating implicitly. So then y prime is equal to 1 over the cosine of y.
What'd you do in the first step to get sin of y equals x? You just divided by.
It's just the inverse function relationship. Basically, this is what we normally would start with. This is just showing how we get to the derivative of this, basically. Now, because of cosine of y being in the denominator here, okay, cosine of y cannot be equal to 0, but we don't have to worry about that anyways because we're only on the interval from, where is it, negative pi over 2 to pi over 2, okay? Which means cosine can't be 0 because it never actually is those values, right? It can be really close to it, but it's not actually those values. So the cosine of y is not equal to 0 for minus pi over 2 less than y less than pi over 2. And specifically, we can say that the cosine of y is positive on that interval. So, by using a Pythagorean identity, we can actually replace the cosine of y with the square root of 1 minus the sine of y squared. So the sine of y would be squared, which is just when we have cosine squared plus sine squared equals 1, that's where this is coming from. We're basically just solving for cosine. Now, going back all the way up here, we said that the sine of y is equal to x. So, this means this is the square root of 1 minus x squared. So ultimately, or therefore, d dx of the inverse sine of x is equal to 1 over the square root of 1 minus x squared.
Could you scroll up a little? There's that bag of styrofoam cups is in the
Oh yeah, I can also move those. So now y'all could do that on your own, right?
No.
Okay, good, because you don't have to.
Yeah, I'm kind of confused, so I need to probably.
I wouldn't make you do this by yourself. All right, now I'm going to show you what the chain rule would look like for this one. So if u is differentiable or I guess I should say is a differentiable function. Of x such that the absolute value of u is less than 1 we apply the chain rule which is going to work the same way as it did in the last section or 2 sections ago when we learned it, but basically d dx of the inverse sine of u is equal to 1 over the square root of 1 minus u squared. And u is whatever that function is. We would actually be writing that function in there. Times du dx, which means the derivative of u with respect to x. So whatever the derivative of that function was. And again, we would specify that this is such that the absolute value of u is less than 1. All right, so that's arc sine. Now, in a little bit, when we get to the end, I'll explain to you how to get the other, like the 3 that are the negative ones, but we're going to do all the positive ones. So the derivative now of arctangent so y is equal to the inverse tangent of x is defined for all real numbers and is differentiable at all real numbers. So we're going to start with y is equal to the inverse tangent of x. So the inverse relationship of this is going to be that x is equal to the tangent of y. Actually, I'm going to write it the other way. Tangent of y is equal to x. Doesn't really matter, but just to keep it consistently going down. So then, and this is the inverse relationship again. So then we take the derivative, okay, implicitly. So what would the derivative of the tangent of y be?
Negative
Negative cosecant.
No, it's secant.
Secant what? Secant squared. So it'd be secant squared of y implicit
Y prime.
y prime is equal to 1. What?
We got like 20 minutes left in this class, I think.
Correct.
I'm ready to leave.
Christian said there's 20 minutes left.
Christian.
Are you going to do all 6 of these
No, I just said we're only doing 3 of them.
for now?
No, like we will only do 3 of them.
Hang in there, Christian. Let's go. We're on the second
We're
one.
on the 3rd page.
Oh.
Alright.
You're lying.
I'm not.
Third page.
This is after this. After we get through this one, this is all we have left.
Okay.
I thought you
Let's
said
get through it.
3.5 pages. Maybe
Yeah.
I'll just review.
Yeah.
Alright.
All right, so y prime is equal to 1 over the secant squared of y. Now, do we remember what the what is it called? Pythagorean identity is that relates secant?
Cosine over sine.
No, the Pythagorean identity. Like sine squared plus cosine squared equals 1. What's the one that involves secant?
Tangent square plus
It's
Yeah. Secant squared. Secant squared is equal to tangent squared plus 1, or 1 plus tangent squared, I think is the way it technically usually gets right, and it doesn't really matter. So now I can replace secant squared with this 1 plus tangent squared. So 1 over 1 plus tangent squared of y. I'm actually going to write it this way so that you can see it. Tangent of y, we said, is
arctangent of x.
tangent of y is equal to x. So this would be equal to 1 over 1 plus x squared. And this is defined for all real numbers.
that one was a lot easier than
The other one would have been easier if I just did this and didn't explain every little detail.
Oh.
There.
Okay, yeah.
So now, again, I'm going to do the applying the chain rule part, but I'm just going to write chain rule for this one. Would be d dx of the inverse tangent of u is equal to 1 over 1 plus u squared. Again, remember, u is a function, times du dx, and then the derivative of u with respect to x. One page left. You power through.
Ooh, power forward.
Ethan's favorite words. All right, so we've done sine or arcsine, arctangent. Now we have
Secant.
arcsecant. So this one's a little more in depth, but still not bad. And again, I'm not going to ask you to rederive these for me on the test. I'm just trying to show you where they come from and why.
Just memorize them so you don't have to do them. I feel like it's easier to memorize them than remembering how to derive them.
Oh yeah, I would never derive them otherwise.
No.
But it's good to know where they came from and how to.
Yeah.
We're basically doing college level proofs right now.
Oh, you have to do this.
Mm-hmm.
When you put
You
it
to be
like
like,
that,
oh, what's like why is
Couldn't tell you.
what of that?
Couldn't tell you.
Oh, that's
They're like
terrible.
real world application. I'm like, no.
that was the real world application.
Of like how this came to be, like why is this coming?
Thought of it.
These are gonna be the
What
grocery.
How a particle
prices.
moves.
Who invented derivatives?
I'm not gonna lie. There's not real world application to these problems in the
The
book,
man
so I don't
who
know.
gave us derivatives.
These are gonna be the grocery prices listed in the future. That's why we have to know.
Yeah, right. So we're gonna start out with y is equal to, or well,
Edmund
Yeah.
O'Connor.
What's his name?
inverse secant of x for the absolute value of x is greater than 1. So the first step is secant of y is equal to x, which is the inverse relationship. Now I'm going to take the derivative implicitly, which would be what?
Secant of what? Tangent.
Implicitly,
And then the thing.
y prime equals 1. So this is differentiate implicitly. So y prime is equal to 1 over the secant of y, tangent of y. Now, something to note about this, since the absolute value of x is greater than 1, y lies in 0 to pi over 2, union pi over 2 to pi, and secant of y, tangent of y is not equal to 0 because of that. That's why we've removed pi over 2, as well as 0 and pi, because both of those would cause problems. But everything in between those is fine. Good. That's what I thought. So I looked back there. I was like, okay. All right, so we know that secant of y is equal to x, and tangent of y would be equal to plus or minus the square root of secant squared of y minus 1 from a Pythagorean identity. So we would then have that this is equal to plus or minus the square root of x squared minus 1 okay, because we replaced secant of y with x and it was squared, so that's where that comes from. So now y prime is equal to plus or minus 1 divided by now normally, well, let me do it this way. Yeah, I'll do it that way. Okay. Plus or minus 1 over x times the square root of x squared minus 1. So we still had secant of y on the bottom, which is what x is, and then we used this manipulated stuff for tangent to get this part.
Okay.
So secant of y is x, tangent of y is the square root of x squared minus 1.
I was confused for a second.
That's why I was debating how I wanted to write it, because there's something else that can go with it, but then I was like, well, I'll do this part first, and then we'll...
I was confused for a second, because I was like, where did you just spawn the x? Part of the square root. And then
Yeah, I was like,
oh, wait, let's
hmm.
take it.
Yeah.
Like, what? What's going on? Came out of nowhere.
So then the other way that we sometimes will write this is because we want to eliminate having to have this plus or minus, is we will actually write d dx of the inverse secant of x is equal to 1 over the absolute value of x times the square root of x squared minus 1. Because it basically just removes the potential, like, confusion with that, because it needs to be positive for that situation. So anyways, it just eliminates the issue. I often don't write the absolute value, but it technically is supposed to be absolute value. So then the... what color have I been doing that in? Chain rule. For this would be d dx of the inverse secant of u is equal to 1 over the absolute value of u times the square root of u squared minus 1 times du dx, given that the absolute value of u is greater than 1. I would say to eliminate the confusion, go back and put absolute value bars on the ones that we did up here, just so that there's no issues with you getting signs wrong, because this is supposed to be like this. All right, and then the last thing, the derivatives of the other three. Inverse trig functions. So again, another way that you could do them aside from what we just did, but that would be basically we're going to use the inverse function and inverse cofunction identities. So the inverse cosine of x is equal to pi over 2 minus the inverse sine of x. The inverse cotangent of x is equal to pi over 2 minus the inverse tangent of x. And the cosecant of x is equal to pi over 2 minus the inverse secant of x. Now, just so you are aware, if you were to do these on your calculator, the calculator conversion identities we've got the inverse secant of x is equal to the inverse cosine of 1 over x. Okay, because there's no inverse secant button, there's no inverse cotangent, and there's no inverse cosecant, so this is how we would input them. For cotangent, we would do pi over 2 minus the inverse tangent of x, so that one will look the same as it did up there. And then the last one, cosecant, the inverse cosecant is equal to the inverse sine of 1 over x. All right, and that is all of it. So we'll do a few problems tomorrow. It's not really many, but we'll do a few, and then we'll be done with this section.